Our first application for derivatives is going to be optimization. This is where we'll be determining the best solution to a problem. This will be a minimum or a maximum value of a certain situation. Now, we've definitely seen this sort of thing before with graphical analysis, and we'll use many of those same tools to help us find these solutions. Now, the first step is to make sure as we read the situation that we draw a picture, label it, and try to find relationships, knowing what the given information is and, of course, what we need to find. Now, what's important to understand is that as you read that information, there will be a primary equation. This is the main thing that you want to optimize, whether it be area, length, volume, whatever sort of relationship. That's our main idea. But at the same time, we will also sometimes have a secondary equation. And the secondary equation is used to rewrite our primary as a single variable. Often the geometry that creates this primary equation involves multiple variables, right? Multiple measurements. And so if we're going to use our derivatives and be able to solve and find where these mins and maxes are, we want to use a single variable because that's how our differentiation works. So we will have additional information, another piece of information, our secondary equation, if you will, that will be used to do that. And you'll see that in action in a moment. Now, the next thing is to make sure we check the domain of the problem. This really doesn't always play a very big role, but sometimes, depending on the models in certain situations, some outcomes, right, some solutions that work out algebraically when you're solving don't make sense in the problem. So we always want to pay attention to what kind of values make sense. Usually they're positive values, but also ones that aren't too big that don't make sense. Now, what's going to happen, of course, is that we're going to do the same process we did before when we did graphical analysis. To find our minimums and maximums, we're first going to find the critical numbers. Secondly, though, we're going to verify that those critical numbers are the minimums and max that we're looking for. We can't simply find critical numbers and blindly accept them as answers. We want to make sure that they are, in fact, a minimum or a maximum, so they are the correct solution for the problem. For our first example, we have two positive numbers where the sum of the first number and twice the second number is 108, and we want to find the maximum product of these two numbers. So to begin, normally I would say we'll draw a picture. This doesn't really lend itself to that, but I can start right away and say, what is the main thing I'm trying to solve? Well, I'm trying to find a maximum product. So I'm going to write an equation and just call it P. And of course, it's the product of these two unknown numbers that are both positive. So I'm just going to call them X and Y. So my main primary equation is right here. I have the product of these two numbers, and I want to find its maximum. Now, the secondary information I'm given, of course, is the idea that the sum of the first number and twice the second number is 108. So kind of off the side, I'm just going to say that my first number, I'll call it X, and my second number, Y, if I double that, if I add those together, that right there is going to be 108. Now, what this does is it gives us a relationship between X and Y, and more importantly, allows us, using this equation, to rewrite this using only one variable, okay? Now, you can pretty much choose to either go all in X's or Y's. I often look at my secondary equation and ask myself, what's the easiest one to solve for? Here, I would definitely suggest getting X by itself as the easiest. So by simply subtracting 2Y from 108, I have an expression for X here in terms of Y. So what that means I can do is I can actually update my primary equation to not just be X times Y, but only be in terms of Y's by taking this expression and replacing it here with the X. So by doing that, what's going to happen is instead of writing X, we have that 108 minus 2Y and multiply times Y. Now we can, of course, clean this up a little bit, because we're going to find the derivative. So if I distribute, we'll get 108Y minus 2Y squared. So of course, if we're looking to find the maximum value of this, we want to look for its critical number. Okay, so in this case, looking at this right here, if we find the derivative, we're going to solve that for 0. So P prime is going to equal 108 minus 4y. Now when I set that equal to 0 and figure out the value of y that makes that happen, we get y equals 27. By subtracting and dividing. Now when I do that, again, that is my critical number, but we can't just blindly assume that is, of course, going to be our max. We want to verify that to be the case. And we do that by using the first derivative test. So that means we're going to look at the signs of the first derivative around 27. Now this is where we can also ask ourselves about the domain. And the original problem does state that the two numbers must be positive. So that tells me that they have to be greater than 0. There's no maximum, value as far as what they could be, but obviously we can't have any negative values. So choosing values on the both left and right sides of 27 and plugging them into the first derivative, we do discover that numbers between 1 and up to 27 are positive. On the other side, they're negative, which does in fact verify that that is a maximum. Now, the last thing to keep in mind, of course, is that the critical number may or may not be your actual answer. Here, we're looking for what these two positive numbers are. Y is only one of those answers, okay? So my last step is to take the 27, okay, and the solution I found, and basically plug that in right up here so I can actually figure out the Y value. Because at the end of the day, the answer to this problem is going to be a value for X and Y, right? The two positive numbers. So again, we already know that the Y value is 27, and when you plug it in over here and figure out the X, we get the value for X to be 54. Now let's try a problem asking us to find the maximum area of a rectangle with a given perimeter of 100 feet. Now this time, of course, it may make sense to make a picture, although this is a pretty basic situation, but it's a good habit to make pictures to make sure you identify correct geometric relationships. So we have a rectangle. I do not know the width nor the length, so I'll just simply call those X and Y. And our primary objective here is to find the maximum area. So my primary equation is going to be A equals XY. Again, that's how you calculate, the area of this rectangle. Now, my secondary equation, my other piece of information is the given perimeter. Okay, so we're going to work with area, right? That's our main idea. But given a perimeter will help us rewrite this in terms of a single variable and give us the constraints on the actual, measurements. So when we look at the secondary equation, the perimeter is going to be 2x's plus 2y's, and we know that needs to be 100. Well, first off, I can divide all this by 2 to know that x plus y must equal 50. And after that, it's really my choice on what letter I want to solve for. So this time, I'm going to solve for y. So that means y is going to equal 50 minus x. Now, what I can do, of course, is take this expression here for y and replace it in my primary equation. So now I can rewrite my area not to be x times y, but to be x times what y is, which is 50 minus x. And of course, distributing gives me 50x minus x squared. So now that I have my primary equation in one variable, we can find the derivative and solve for 0. So the derivative in terms of x is going to be 50 minus 2x, and when you set that equal to 0 and solve, we're going to get a value of x equals 25. Now, of course, just because we found our critical number doesn't guarantee it to be the answer. So as always, we're going to use our first derivative test, and we're going to check. Now, first off, these are measurements of a rectangle. They clearly need to be positive numbers. But when you think about having a given perimeter of 100 feet, what we know right away is that if x plus y, right, can only equal 50, that means when we talk about the area and stuff in general and the values of x, that means that, altogether we're going to have a constraint on what x can be. Now, since we're talking about maximum value as far as having a domain, the absolute biggest value x can be is up to, but not 50. If we let y be some super, super small number, x is getting closer and closer to 50. So the upper end here is going to be that. So just make sure when you're choosing numbers and looking at it, that's kind of our domain restriction. Whatever x is has to be smaller than 50. Otherwise, we'd run out of amount for the perimeter, but it definitely has to be positive. So testing values in the first derivative here on the left side of 25 do in fact give us a positive numbers, and then choosing numbers that are greater than 25 in the derivative does give us negatives, which does verify that is a max. Now this time, the answer to the question isn't the measurements, right? We're not looking for the actual values of x or y. It wants to know what the actual maximum area is. So we actually don't need to find the value of y. What we can do is we can now take our answer x equals 25 and we can actually plug it in right here, because this tells us what that max area is going to be for any x value. So in doing that, basically plugging in a of 25, okay, and punching that up, it gives us an area of 625 square feet. Now, a similar example here involves, again, a rectangle, but this time what's going to happen is we essentially have a given area, and what we're trying to do is minimize a perimeter, right? In this case, it's the idea that we're going to use the least amount of fencing to enclose it. So it's very similar to the problem we just did, except we kind of flip what the given information is and the thing we're trying to optimize. So first things first, we want to draw a picture. Now this one's important because what's happening is that we basically have a river on one side, and then what we're doing is we're enclosing a rectangular plot of land like this, but we don't need to use any fencing along the river. So we can have a y here, an x here, and a y here. So that means we have a little bit different situation when we talk about the perimeter. So Our primary objective is to minimize that amount of fencing, or in other words, perimeter. So I'm just going to call that P for perimeter. And looking at the situation here, I basically have two Ys and I have one measurement X. That's going to make up the amount of fencing needed to fence this in, since again, we have that river on that one side. Now, my secondary equation is that given information. We know that the rectangular region has to have an area of 405,000 square meters. So that means kind of off to the side, what I know is that if I multiply X times Y, which would give me the area of that rectangle, that needs to equal 405,000. Now, again, when we do this, we want to think about which variable we want to solve for. Here, I think it's pretty easy to go ahead and solve for X. And one of the reasons I think that's easy is not really here, but looking at the equation for perimeter, we have an X by itself. So it makes for the easiest amount of substitution to plug something in there. You could, of course, solve for Y and replace it and double it, but I'm just trying to minimize my work. So that being said, if I go ahead here and say what is X equal to, that's going to be 405,000, and then what's going to happen is we're going to divide by Y. So instead of saying over Y, I'm going to write times Y to the negative first. It'll make my algebra a little easier, but again, we're simply dividing by Y. So substituting that now into my primary equation, I can rewrite the perimeter only in terms of Y. So we have 2Y plus, and again, in place of X, we have that 405,000 times Y to the negative first. So we'll find the derivative and solve for 0. So the derivative is going to be 2, and then this will be negative 405,000 times Y raised to the negative second power. Now, what's important to remember about this one is that when we solve for 0, we want to use a proportion, okay? So when I set this equal to 0, I'm going to go ahead now and rewrite this right part of it here as 405,000 over Y squared. Because the easiest way to solve this for 0 is to add this fraction to the other side. So we'll put this thing over here on the left, and then just set that equal to 2. And if you want to write it as 2 over 1 to really see the proportion, that's fine. But what I can do now is cross multiply. So when I do that, take Y times Y squared, it gives me 2Y squared, and then 1 times that is going to give me 405,000. So if I divide by 2 and take the square root, what I discover is that the value of Y here is going to be 450. Now, having done that, again, we still need to verify that it is in fact, the minimum we're looking for. So looking at the signs of the first derivative, obviously we have to have positive measurements. Okay, that makes sense. And it's strange to say, but we actually don't have an upper limit. Even though we have an area that has to be, exactly 450,000 square meters, we can literally let Y be as big as we want because we can let X be as small as we want. Unlike, having an addition situation with a perimeter, because you're multiplying them, you can let X become infinitely small as Y becomes infinitely big and still have a product that equals that. So really on my domain, I just have to make sure I'm positive, okay? So we're going to check numbers in the derivative on either side of 450. So if I choose, for instance, 1 and plug that in the derivative, clearly we're going to get a negative answer. But if I go above 450 and plug in my derivative, we actually do get positive answers, which does verify that is the minimum I'm looking for. So those are going to be the answers to our problem. So plugging it in, okay, we already know that Y equals 450 meters. So we look for the value of X, and we can find that right over here, plugging that in. And it says the value of X has to be 900 meters. Now, for our last example today, we'll look at a distance formula. So again, we could draw a picture, but one's really not too necessary on this because we don't have to, think about any geometry. We already have the exact relationship here. So we have a point, right, that's somewhere on this parabola, and we want to know which point on that parabola, right, is closest to the order pair 1, 4. Okay, so our primary equation is looking for minimizing distance, right? So it's going to be the distance formula. But our secondary equation, the given information, this relationship is going to help me, make that a single variable and give me any constraints. So to begin, we're just going to start using the whole distance formula. Now, the distance I'm going to create between the 2 points is going to be between the point 1, 4 and some unknown xy. So it's going to be some unknown x minus our given x value squared plus some unknown y minus our y value squared. Okay, so that's our setup. Now, the one really nice thing about a problem like this is that if I want to minimize the distance, I don't need to worry about the square root, because if I minimize the stuff under the square root, I will in fact find the same place where it minimizes the overall value. So I can actually, and I'm just going to call this capital D just to kind of notate this a little bit different, I'm going to just work with the stuff under the radical. Because again, if I simply minimize this, that solution will be in the same place as the minimum of its square root. Now my first step, like always, is to get this in a single variable, okay? So what I'm going to do is I'm going to look back at my equation and figure out what the easiest one to solve for is. Well, looking at my condition here, I think the easiest way is to get x by itself, okay? So if y squared has to equal 2x, then I know that x must equal 1/2 y squared, okay? So we're going to put that in place of our x down in the main equation. Okay, so when we do that, what's going to happen is over here we're going to replace our x now with that 1/2 y squared minus 1, and then this right here will remain x minus 4 squared. Now, at this point in time, when you find the derivative, you have a couple options. Clearly, if you want to multiply them out and just do a power rule with those polynomials, that's fine. Personally, I'd prefer not to do all that algebra. I'm simply going to do a couple chain rules. So the derivative of the first quantity here is going to be 2 times all of this stuff raised to the first power times the derivative of the inside, which is just 1y. Then, by chain rule again, we'll take 2 times that whole quantity raised to the first power times the derivative of the inside, which is just 1. So now when I solve this for 0, what I'm going to do is now I'm just going to distribute, combine like terms, and things like that. So if I distribute and combine like terms and put it all together, this entire expression simplifies to be y cubed minus 8. So when I solve for 0, clearly the answer is going to be y equals 2. So let's verify that is in fact our minimum value, right? Or I should say the y value that gives us our minimum. So looking at the values of the derivative, we're going to check on either side of 2 here for a y value of 2. Now, that being said, we don't really have any other restrictions. This is just a point in the plane, which means the value, right, of these x and y's could be positive, could be negative. It's really anything. So I'm going to go ahead and pick any values on either side of 2 to check what's going on. And again, looking back at my derivative and kind of looking at the y cubed minus 8, if I choose, for instance, a number like 0, we definitely get a negative. If I choose a number like 3 or 4, cube it, subtract 8, we're definitely going to get a positive. So it does definitely give me a minimum at that spot. Now, the answer to the question is going to be the point. Okay, so I do need to make sure I have an ordered pair. So my ordered pair has a y value of 2. And of course, if I plug that into my original to figure out what the x is going to be, I just take my 2 square, divide by 2, which means the x is also going to be 2, which means the order pair 2, 2 is the order pair that lives on this parabola and is closest to the point 1, 4.